Okay, so this is the lecture we started on Wednesday, um, warehouse operations, and we specifically talk about the warehouse layout model. We went through the formulation and we explained how it works and the details in terms of solutions. So it's very hard for us to get a solution quickly when you have a very large model. So um, let me skip that. So this is a warehouse layout model. We have one decision variable, and our objective function is to minimize the total expected distance traveled. And that's within the warehouse, from the input location to the location of the item, from the location of the item to the output of the warehouse. So we defined some of the parameters, and we formulated the problem. And we stated that this is a very complex problem when you have a lot of items and also when you have a lot of locations. So that's why sometimes it's not feasible to solve the problem directly by trying to formulate and solve it using a computer because it will take a lot of time. So in those cases, um, we can come up with some algorithms that will allow us to solve the problem that will allow us to solve the problem in a more in an efficient way, not necessarily providing the optimal solution, but providing a very good solution close to the optimal. And we will get that solution very fast because the algorithm will perform really fast and will give you a solution in less time than the actual solver of the actual problem. So that's why we went through this specific heuristic for solving this problem. And one of your problems from the homework was actually using this to solve, to find the location. Um, so, so here's an example, and I also ask you to look at this problem because it's a very similar problem than the one that we discussed in class. And that was the last thing we did on Wednesday. So today we're going to complete this lecture, and I just want to call your attention one more time. On Monday, we're going to have our last lecture for the semester. We're probably going to be making the student evaluations at that time. We're also going to have our review. So anything that we don't cover today is going to be discussed on Monday. But the material that is covered on the third exam is what we cover today in class. So anything that we cover on Monday will be part of the final. If you don't take the final, then you don't have to go over that material. But if you take the final, that will be part of the final. So in terms of the rest of the lecture, I just want to go over some of the storage systems that. Yes, sir. No, we have one more partial and then the final, which is optional. Yes. So, yes, sir. So we're gonna get that. You're gonna get all the results for the final, so you can make your decision. So I'll let you know what's your grade for the class, and I'm gonna let you know how much you need to make. Well, actually, I provide you with the grade for the class, and then I'll wait for you to send me an email to see your, because if you have an 80, there's no way that you with the final is gonna get to an 80. So you should be able to compute those numbers. But if you still have doubt, let's say you have an 87 and you want to take the final and check how much you need to make in the final to go to the next grade, then you can shoot me an email and I will let you know how much you need to make in the final. Yes, sir.
Oh, I was wondering if we decide to take the final and it's lower than expected, do you go to the free scale on our benefit? Or
This is also a question, and I think I answered this question at the beginning of the semester. If you take the final will count. But my experience is that students do better in the final. So I have not seen any student doing worse. So if you take the final, you either stay the same or you improve your grade. Okay, but I don't want you to go take the final, score 0, and then say, okay, count me. No, you have to study. You have to do well in the final. Any other questions? Okay. So in terms of star systems, we discussed some of these items in one of our lectures. Um, but I want you to focus on these items specifically for warehouses. So first one is the rack storage system. And this is one of the primary methods of material storage. It utilizes the vertical space in the warehouse, and it is highly cost efficient. So we have different type of racks. First one is the walk-through racks, pushback racks, very narrow aisle racks, driving racks, and the gravity flow racks. And I'm going to show you pictures of those in a second. Mobile racks, double deep racks, roll-up shelf racks, video racks, and cantilever racks. So this is a walk-through rack. You'll see you have an aisle in between, so you can move through them, and also in a parallel fashion. And you can storage items in a lot of different places. So this gives you a lot of space. So provides easy accessibility to adjacent aisles. Picking time is greatly reduced. Allows more lighting into aisles and have higher utilization of the vertical space. Most of the time when you have these aisles, you will have all the space above the aisle open. This particular type of rack will cover that area, and also you will use that area for storage. The pushback racks, so you're essentially putting the items from this perspective and then pushing back. You can see how that's working right here. So you have the forklift pushing the items. The features, pallet loads are literally pushed back into the rack. When pallet is retrieved, the deeper pallet load automatically advances to the aisle. High density and high accessibility, used to store large number of pallets for a long time, and then remove and ship them as seasonal products. And is used mostly in combination with driving racks. Here's another type of rack. So this is a very narrow aisle rack. And as you can see, you have a very limited space in between the racks. You have the operator going through the items using this equipment, which is similar to a forklift, but you have stations that will put you on top of it. And for this type of warehouse system or storage system, this permits aisle width less than 5 feet. So again, very narrow area. Provides significant floor space reduction. Use at heights of 40 feet to 50 feet. Pallets are accessed with turret or side-loader lift trucks, and sometimes racks are designed with the top and bottom monorails. Then we have the driving racks, in which you can go with the forklift. This one used for bulky and lightweight parts. Parts are mainly in cartons. Forklift is the material handling device used, and parts are typically stacked one over the other in large numbers. Here's the gravity flow rack. This works. There's some of the soda machines that usually still use this type of um, gravity flow in their design. And the idea is you have some type of inclination here. So when you pull one of the items, the other one will move to the front. Um, so used for parts in cartons, parts are supported on rollers in the rack system. Material transfer is done with easy to move parts along the same row, and as less effort is required due to the presence of the rollers. Another type of storage system is called the mobile racks. So for this one, I think the best picture to show how this works is this one. So you can push these racks and you can move them according to your need. So that also saves you a lot of space. So if you need to move in between these two racks, then you can push them or pull them, and you can get access to the item that you need. So this is some of the features: high density storage system, 100% utilization of pallet positions. Storage carriers are driven by electric motors used mainly in cold or ultra cold warehouses where aisle space is a premium and used when the speed of product movement is not a major concern. Another type of storage system is called the double deep racks. Um, for this one, it's like placing two rows of racks together, like the one we're seeing here. Uses deep reach lift truck for storage and retrieval. Increases the floor space of usage to about 60 to 65%. Used for high throughput operations, low initial cost, high productivity, and less equipment damage. This one are for starting parts that are, I would say, expensive, delicate. So this is called the rollout shelf rack. This is for specialized storage, mainly for dedicated and costly parts, and used for dies measurement tools. So again, some of them will contain some doors, so you can close them and store them. Um, some of them will be open like this one. And then we also have some real racks. So the idea is to have those rolls, and you can pull whatever you need in terms of material when needed. Um, so this is a special type of storage, mainly for cables and wires in reels. The cantilever racks, as you can see, this type of storage system. If you go to the Home Depot or Lowe's, they use them for construction materials. So the idea is that you have a flexibility. These are very long. Could be wood or any other thing. So used to storage long pipes or wood. Parts are stored using the forklift, highly economical, and can be used steel heights of 22 feet. In terms of carousel storage, some of the advantage, high peak rates, motorized computer control, and independent rotating aisles of shelving. Parts are carried back to the picker rather than the picker, going to the parts like in the case of racks. Monthly set up in pots of 2 or 3, and pick rates vary from 800 to 200 picks per person an hour. And I don't think I put a picture of that one here. Adding more space, I'm sorry, these are disadvantages. So adding more people cannot significantly increase peak rate. Only one picker can operate at a given time, thus reduce the ability of the warehouse to respond to surge in demands. And here's one of the of the carousel. So in this one, this is also very similar to the system that we use in the laundries. So you have this engine moving the carousel and will stop in this position when you get to the part that you need. So it's easier for you to pick the items. And that's why we say adding more people would not improve the efficiency of this system because you only have a limited space to do the picking. So series of rotating beams of adjustable shelf driven at the top or bottom by a motor. Rotation takes place on the basis perpendicular to the floor, about 80 feet per minute, and horizontal length varies from 15 to 100 feet. Height varies from 6 feet to 25 feet, and price start from 5,000 and increase with the number of beams and weight capacity. Finally, we have the automated storage and retrieval systems. We showed a couple of pictures of this one in our previous discussion. This one will move automatically with programs. This improves space utilization. 70% of rack space can be recovered. High saving in pickers time allows for quick access to goods via a system of shelves operating on a shuttle mechanism, and it brings the exact pick store location to the operator, increases retrieval productivity for more than 2.5 times. Another good thing about this type of system is the access area of the system is ergonomically designed to present stored items at an ideal height for picking and high employee safety and improved throughput. So here's a picture of that system. So this will move the items that are needed by the operator, and will then bring them to the location of the operator. And you'll see the items located in both sides of these racks. Okay, so that ends up our discussion in terms of the warehouse planning, storage systems. So this is going to be part of the third exam. Now we're going to transition to a different topic. Which is single facility location models. And again, in this lecture, we are no longer thinking about how to design the facility on the inside. Now we're going to move and talk about where do we need to locate our next facility. So this is the type of models that we are going to discuss. Today, I'm going to show you one of the models, but there's multiple models that are available for these type of decisions. So this is going to be part of the first objective of your course. Excuse me, develop an understanding of the principles of facility location. So we're going to look at that item specifically, where to locate a facility. So I'm going to provide you with an introduction, and then I'm going to explain the single facility location model. The objective for this lecture is for you to learn one of the facility location models and understand the results that the model will give you. So as I mentioned, there's several types of location models that are available. For instance, there's the single facility location model, the location allocation model, and the quadratic assignment model. All of them will look at the problem from different perspectives in terms of how to compute the distances from the existing locations to the new location. Some of them we consider rectilinear distances, meaning that you're moving in perpendicular way and vertical, horizontal and vertical way. You don't have diagonals. Some of them we look at the diagonals to compute the distances. Some of them will go more in detail and will find the actual distance in terms of the roads that you're planning to use. So those are very descriptive models. So the model that we're going to discuss today is for planning for a new location. The idea is you have several locations around a specified area, and you want to know based on those locations, those could be clients, could be storage warehouses, could be any other manufacturing plant that you need to be close to. And then you're going to decide, okay, based on those locations, I need to put my next facility here. Or based on these locations, I need to put the next facility in this area. So again, we're going to focus only on the first one, this lecture. We're going to look at the single facility location model. And we have two approaches for solving this problem. The first one is called the mini location problem, which basically look at minimizing the sum of the weighted distance between the new facility and other existing facilities. So you're going to have the location of the existing facilities, and you're going to provide the model with the weight in terms of the importance for you to be close to that facility. So let's say you have 5 locations, one of them is more important than the other, then you're going to provide that weight, a higher value, because you're going to push the model to locate you close to that one in particular. And then the second approach is called the minimax location problem, which is minimizing the maximum distance between the new facility and any existing facility. So again, I want you to be able to understand the difference between these two. The first one, you're providing a weight. You're actually telling the model these are the ranks for the existing facilities in terms of your decision. I want you to be closer to this facility than the other one. We're providing those weights in terms of importance. The second approach is looking at the maximum distance between the new facility and the existing facility. So you can think about this type of problem. If you want to allocate, let's say, a fire station, you want to minimize the maximum distance between the new facility and the existing. Because you want to be able to get to multiple locations in the minimum time. So you want to shorten those distances. So that's why we make those differences. So in terms of rectilinear distances, this is how are we going to measure our distances from one location to the other. So what I mean by rectilinear distances is that we're going to look at the vertical and the horizontal line in order to compute the distances. So if this were location let's say this is facility 1 and this is 2, and this measured 3, 4, 3, and 5, then distance between 1 and 2 will be 50. Okay, because we are looking at the total of distances of those lines. Okay, so here's a description. So we have the existing facilities are denoted by those yellow circles. Okay, and we are going to add a new facility, which is here, this red circle. want to compute the distance between this facility, this existing facility, and this one, so we're gonna use these parameters to define our model. So we're gonna have y and x. Y and x are the coordinates of the new facility. A and B are the current location or the current coordinates of an existing facility. Okay, so if I say A and B are known because this facility is already located, we know the location of that facility. What we don't know is the location of the new facility. Okay? So that new location, you're going to find that location by solving the problem and finding x and y. Okay? So if we want to compute the distance between, let's say we are going to assume that the new facility is going to be located there, we can compute that distance by looking at x and y, b and a, by using that equation. So the distance is going to be the absolute value of x minus a plus y minus b. And we can find all the distances from this new location to all the other existing facilities by using that same approach or that same equation. So if let's say a is 15, this is 10, 0, this is 5, and this is 10, then the distance is going to be equal to the absolute value of 10 minus 15 plus the absolute value of 5 minus 10. So this is 10. Okay? This is very important. So I want you to understand what we're trying to do. We're trying to locate a new facility. We don't know the coordinates of that new facility, but we know the coordinates of the existing facility. And so if we assume that the location of the new facility is there, we can find the distance, direct linear distances from the existing facility to the new facility using that equation. Any questions so far? Okay, so remember we are going to use we go back here, the mini-zoom approach. So we are trying to minimize the sum of the weighted distance between the new facility and other existing facilities. So we need to provide a weight for those distances. And we can name those weights W, which is going to be the number of trips from the existing location to the new location. Okay, so that's going to be our WI. So for the new facility, WI will apply the same value for both segments. So this W is the same as this W. So we are going to have a weight from this point to this point. So the weighted distance is basically multiplying the weight, which is again the same weight for those segments. You're going to multiply the weight times the distance, the horizontal distance, plus the weight times the vertical distance. And that's going to give you the weighted distance. And then we can solve or formulate our problem. So we are going to minimize the sum of the weighted distances, which is here. And we're going to have two constraints. Actually, we are looking only into the objective function right now. So what I'm showing here is that we can separate this objective function into pieces because there's no part of this equation that are the same as this part of the equation. So we can take this function in terms of x and y and separate the model in two pieces. So we can focus only on the vertical distances, and we can also focus only on the horizontal distances. So that's why I'm calling that function a separable model. And here we have same slide. We have the function in terms of both. You can separate that function, and then we can focus on minimizing the distances for the horizontal distances and also focusing on minimizing the distance in terms of vertical distances. So here's an example. We have facilities 1, 2, 3, and 4 allocated at the point A5, which is this one, 4, 2, which is this one, 11, and 8, and 13, and 2. So we have those facilities. Those are existing facilities. And we want to be able to allocate our new facility using that information. So we also have, it is estimated that there will be 9, 6, and 4, 9, 6, 4, and 12 trips per week, respectively, between the facilities and a proposed new facility. And the question is, find the location of the new facility. So we can take this information, we can formulate our objective function using the details. So as you can see, we have one of the first part of the objective function is only with x values or with the x variable. So we start with the weight of 9, which is for the first number of trips from the facility 1 to the existing facility, existing facility 1 to the new facility. So that's 9. We also have the weight from the second facility to the new facility, which is 6. The weight from the third facility to the new facility, and so on. So when we focus on the first facility, we are trying to define our function in terms of that first facility. So we're going to look at the weight and also the coordinate of that facility in terms of x. So that's why we have 9 times the absolute value of x minus 8. We repeat the process for all the facilities in terms of x. So that's what you have here in this first portion of the objective function. So all this corresponds to x, or the x coordinates. And then we have the function in terms of y. So instead of looking at the x coordinate, now we're going to look at y coordinate, and we're going to formulate that. So that's why we have y minus 5, y minus 2, which is v2, y minus 8, which is v3, and y minus 2, which is v4. So this is our objective function for this problem. If we solve this problem, then we're going to obtain a formula, value of x and the value of y, which is going to give us the location of the new facility. So we can reformulate this as an LP problem. So if we let x minus ai be equal to ri plus si, then here we are looking at the absolute value of that expression. If we remove that, then we can say that this is going to be equal to ri minus si. And we can use that information to state the objective function. This is in terms of x. So we are trying to separate the model for x, and we are substituting this using this formula. So x minus a will now be in terms of the first facility. So this will correspond to this portion of the equation. X minus 4 will correspond to the second facility. X minus 1 will correspond to the third facility, and x minus 13 will correspond to the fourth facility. And we can also set up our constraints in this form. So the first constraint will correspond to the first facility, and we know that this is going to be equal to the location of the, in terms of x, of the existing facility. Okay, so what I'm showing you right now, this is the format that you're going to use to formulate this type of problem. Okay? So the first facility will look at this first constraint, and it's going to make that equal to the coordinate of the first facility in terms of x. And we are going to repeat that process for the second existing facility, the third existing facility, and the fourth existing facility. So we have formulated the first part of the problem. Now we're going to repeat the process for minimizing Z2, which is going to be in terms of the y coordinates. So we're going to have y minus bi equals to ri plus si. And now this will correspond to this. This will correspond to this. Okay, so we started with our objective function that will consider both coordinates x and y. Now we are separating the model. We're focusing on, we're basically formulating the problem just for x and formulated a separate problem just for y. We are substituting x minus ai by this expression, ri plus si. So that's what we have here in the objective function. And you will see now why you're using the same substitution for the problem in terms of y. So the coordinates will have those, the constraints will have the same parameters. The only difference that we're going to have is the coordinates in terms of x and y. So this is our second problem. Second separated problem. So half of the problem is solving for y, half of the problem is solving for x. So once we have this formulation, we can just take this to one of our solvers like Excel, Lindo, Cplex, and get a solution in terms of x and y. That is not part of this course, but what I'm going to show you is how to formulate the problem and how to get a solution using one heuristic. Okay, so we can solve this using one of these solvers. If you take the class IT 334, I teach you how to use Excel to solve these problems. Also, sometimes I teach Cplex. And what you do is you formulate the problem in this form, and you give this format to the computer. And the computer will read this and will provide you with the solution. So we have two formulations. The computer will give you, based on the first problem, what will be the x value. In this case, x equals 11. That's your first coordinate. And you have an objective function of 93. And then you solve the problem in terms of y. The objective function will be 51. So the optimal solution for this problem will be locating the facility in this coordinate, 11, 2. And that would provide you with a cost of 144. So again, we are trying to minimize that cost. So this is the optimal solution. This is the best place for you to locate the facility. It's on the weights that you have provided to the model. Okay, so but for the purpose of this course, before we get to the algorithm, what we are saying is these are the existing locations of the facilities, and we're going to place the new facility here. Okay, so that's the solution we obtained. Based on the information that we have of the existing locations of the other facilities, the weights in terms of distance travel from one location to the new location. Using that information, we got that the best location for this new facility is 11 and 2. Any questions so far? Okay, so I show you how to formulate the problem. I show you that you can solve this problem using one of the software. Again, when you generate a problem, let's say instead of having 4 facilities, we have 50 existing facilities. And you're trying to find the best location using those 50 clients, for instance. The problem will become very large, and it will take a lot of time for the computer to solve those type of problems. So that's why we devised an algorithm to try to get a faster solution using the information that we have from the problem. And the algorithm, this is what you need to know for solving this type of problem. It's called the cumulative weight algorithm. And what this algorithm does is it will take into account the information of the facility. So, for instance, we have facility number 1. These are existing facilities. And it will use the value of A1 and B1. Again, those indexes correspond to the facility number. So these are the location or the coordinates in terms of x1 and x2 for the first facility. And we also have a weight in terms of the distance travel or the number of trips for the existing location to the new location. So we need to make sure that we have that information in order to apply this algorithm. So you need to have the location and also the weights for each one of the facilities. Okay, so to find the coordinate for the new facility in terms of x, we're going to use this information and this information. H, the H, and the W. And to find the values in terms of y or the coordinate for y, you're going to look at the b values and the weights. So the rules to determine the optimal value of x, you're going to arrange the a's or the ai's in increasing order. You're going to compute the sum of weights or trips for each value. And the optimal x is the value at which the cumulative weight is greater or equal to the half of the sum of the weights. Okay, so the best way to solve this problem is to have a table with all the information that you need. For instance, you're going to need to compute the sum of weights after you arrange the existing facilities using an increasing order of the AI. So you put that in order, and then you compute the sum of the weights. And then you find the optimal x, which is the value at which the cumulative weight is greater than half of the sum of the weights. For y, we go through the same process. The only difference is that we are going to look at the b values in terms of, instead of the a values, we're going to put the b values in increasing order. We're going to compute the sum of weights for each value. And then the optimal y is the value at which the cumulative weight is greater or equal to half of the sum of the weights. So here's the, again, we are going to solve the problem for this data, which is the same data that we have for this problem. And we're going to check if the algorithm is going to give us the same solution as the software. So first, for calculating the optimal x or the coordinate for the new facility in terms of x, we arrange the facilities in terms of the AI values. So again, these have to go in increasing order. So 4, 8, 11, and 13. That puts facilities in this order. So the first facility is 2, the second one 1, third one is 3, and the fourth is number 4. So again, this order is coming after arranging those in terms of increasing order of the AI value. Once you have that, then you know the WIs for each one of the facilities, and you can compute the sum of the WIs using this information. So you just go and add 6. This one is 6 plus 9, so 15, and so on. So your 15 plus 4 is 19, and 19 plus 12 is 31. So that's how you compute that last column. Is the cumulative of the WI values up to each one of the facilities. Any question about how to get those numbers? Because once you get those numbers, the rest is very easy. So one more time, you erase this. You have this order. You're going to use the corresponding weight for each one of these facilities, and then you're going to obtain the sum of weights, which will go up to this point for this one, up to this point for this one. So the other thing that you need to compute is the half of the sum of the weights. So again, the sum of these weights is 31. So if you look at the half of it, that's 15.5. And now you're going to use this number to determine the x coordinate. So 15.5. So using this information, now you're going to compare this number with these values. So what you said is if 6 is greater than 15.5, no. 15 is greater than 15.5, no. 19 is greater than 15.5, yes. So we stop here. Yes, sir.
We discussed that the first one is greater than or equal to the value?
Yes, that's correct. So x star will be this coordinate. Okay? So you compute this value, you check the sum of the weights. Once you find one that is greater or equal than 15.5, you assign that coordinate that belongs to that vicinity to x star. And now we have to repeat the process for the coordinate for y. So we have the facility I. Again, you're gonna sort them based on the values of B. Here, as you can see, you have two facilities that have the same value for that coordinate. So what you do is you look at the value of the facility and you put them in that order. So these two have the same value, so you go first with 2 and then 4. And you have the weights, and then you also have the sum of the weights. So we repeat the process. We already compute this. Half of 31 is 15.5. So if you follow the same process, the first number is going to be greater than 15.5 is 18. So our coordinate for y for the new facility is 2, which means that the optimal location of the facility will be 11 and 2. If we go back to our optimal solution here, that was the same solution that we got using the software. So as you can see, these algorithms could be really, really good. They will allow you to find a solution easy, and you'll get the same solution, which is the optimal solution for most of the cases. So that's this is called again the cumulative weight algorithm. And that's how it works. So any questions? Yes. So everything that we cover up to today is going to be part of the exam. The exam is going to be not, well, after Thanksgiving, the Wednesday after Thanksgiving. And I think that's all I have for today. So if you were to allocate that, again, it's the same location, and the optimal solution is 144. Any questions? Yes. The last problem of the homework. Yes. Okay, so this is the third problem. We have an existing warehouse that will be used for storage of fixed quantity. Warehouse consists of storage space of 20 by 20. Someone has been designed, designated as the receiving dock by docking used as the receiving dock. The area requirement and monthly load rate for each product family are shown in this table. And the first thing we have to do is to formulate the problem using the model discussed in class. So your question was for the first part or for both? Okay, so in order to formulate the problem, you just have to use the same format that I gave you in class. The only thing that you have to substitute is the values that were given. So now you have 6 products. I think you only have 2 in the problem that we discussed in class. And the information also in terms of the area. So it's nothing different. Then we have the same objective function and we have the same constraints. The only thing that you need to make sure now is that you go from 1 to 6 and you have 32 locations for your warehouse. And for the products, you have to make sure that you satisfy that same requirement for all your products. Okay? So it's the same model. The only difference is that now you have to make sure that you are accounting for the right number of products and the right number of locations. Yes. Yes. No. Yes, you use the same probability. That's correct. So you use the same probability, and you have to determine the layout that will minimize the total expected travel distance. So you're gonna rank the product again, and you're gonna look at you're gonna use the algorithm to solve the problem. So you have to look at the ratios, and then rank those products in terms of that ratio. And then you also need to find the distances for each one of the locations and then start allocating based on those ratios.
Wait, how do you figure out the estimates?
The number base are based on the size of the product. So you have 20 by 20 and you have the area of the warehouse.
Area side by
Say it again?
Is S the area divided by the load rate? Or just divided by the square?
Yes.
Can you go down?
What is the attendance sheet? Anyone else submitted the homework? If you don't have any other questions, you can. Yeah, that's what's going to determine which product is going to be assigned first to the. So you're going to have a grid like this one, and you're going to determine what is the best location based on that grid, and then you start assigning them based on those locations. So let's say you have this grid. And you determine that this is the first best location, this is the second best location based on those distances. So based on this ratio, the largest one is 200. So you're going to start with that one and you say, okay, I'm going to put, let's say I require 6 locations for that product. And I'm going to find the 6 best locations of my grid. So I'm going to put them here, 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 and so on. Then I go to the next and then do the same process.
Can I get me back to, because I did the last part.
Yeah, you can find your homework. Yes, sir. Yeah, I'm gonna try to have them ready by Monday, but yeah. And I'm gonna post the solution today. So.
Oh, you're gonna post the solution?
Yeah.
Oh, then okay.
Yes.
So you just start from the.
You said in the example of the DC equations.
Well, you have to compute the. Yeah. 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 Make sure.
In
that,
the exam, it's gonna be that much.
No.
Oh, okay. Okay.
I still think I'm doing it wrong. I know I sat down with you.
Excuse me. So this is for the previous one here?
Correct.
So which one? The
So
first problem?
I come up with my big F, and then this part, the H1 star, I definitely get. But then after that, I feel like I did it wrong because you said for this one C was 0, I'm getting -3.
Mm-hmm.
So when I come up with H1, it's just H1 star, and then F of 1. Am I doing that right?
Yeah, I think that's the problem. Because you're adding -5 plus 0 plus 0, so that's -1, that's correct. Then 0, 0, -3. Okay, so that's correct. Okay, I'm sorry, that's correct. Homework?
Yes.
So you start with H0 and then you look at H3.
I need help with that.
So this is going to be 0 plus f of 3, which is 4. So that's 4. H of 5, which is H of 2. This is going to be H of 2, which is -3 plus F of 3. Right. So this is H of 2. So you're taking 4 minus 3 is 1. Okay, that's correct. So 0, 4, and 1. Then you go for H1, which is H1. This is 0 minus 5, which is 5. This is 0, 0 minus f, which is 0. And then 1 minus 0, which is 1. And then H2 of 1, This is 0 minus 4 minus 7. This could, and then 3. This is 1 minus 0.
Did you just turn your wind up?
What?
This is 1 minus so this is almost. Okay, so you have 1 minus 3 and 1, that's correct. Just add all these together.